In this video, we discuss the chain rule, which allows us to compute the derivative of composite functions. So basically, anytime you have a function nested inside of another function, this will allow you to compute the derivative very simply. Also, in problems where it would be tedious to actually do the algebra necessary to prepare a function to apply our basic rules, this chain rule will allow us to find that derivative relatively quickly. So let's say I had y equals x cubed plus 5 raised to the 100th power. I could write x cubed plus 5 out 100 times, and then I could multiply the first two binomials, get a trinomial, multiply that by the next binomial, and get another polynomial. And I could do that 100 times. It would be very, very tedious. Or I could recognize this as a function nested inside another function. This is my inside function. And then the outside function is that power function that's raising it to the 100th power. And it turns out that we can compute that derivative relatively easily with what's called the chain rule. So here's the chain rule. I'll just state it. We'll prove it in another video. The derivative of a composite function. We've got f as a function on the outside and g as a function on the inside. Is the derivative of the outside function evaluated at the inside function. So you put the inside function back in, you don't change anything, you just plug it in, and then you multiply by the derivative of the inside. And the notation that we tend to use for this is f prime of g of x times g prime of x. But when I'm actually applying the rule, I have a tendency to write it like this. I use that operator notation where I'm taking the derivative with respect to x of whatever's in the brackets, and then I do the computation on the next line. So this is our rule. And let's say you want to find the derivative of this particular function using that rule. Well, you need to know your basic rules. According to the product rule, or excuse me, the power rule, I've got this function on the outside first. According to this chain rule, excuse me, take the derivative of the function on the outside first. So we say, okay, what is it? What's the derivative of a function raised to the 100th power? Well, it's 100 times that function raised to the 1 less power. So that's to the 99th power. And then you plug the inside function back in. So you don't change it at all. You just write it down inside the parentheses and then multiply by the derivative of the inside. That's what the chain rule says that we should do. And then you evaluate this using your traditional basic rules. The derivative of this one is, well, it's just a power function again. It's the power times x to the 1 less power. So you bring the 3 down, multiply by x to the 3 minus 1, which is 2. And then you add the derivative of 5, which is 0. And of course, adding 0 to anything doesn't change it. So we've got 3x squared times this. I'm going to take that 3x squared and multiply it by that 100. So we end up with 300x squared times the quantity x cubed plus 5 raised to the 99. And that is the derivative of them. So again, remember what it is. Every time we're computing these derivatives with these rules, remember, this is actually a formula for the slope of the tangent line at any x value in the domain of this. The domain of this is all real numbers. So if I want to know the slope at x equals 1, I just plug in x equals 1 here. And this is going to give me the slope. If I want to know the slope at x equals -10, same thing. Plug in -10. This is going to give me the slope of the tangent line as well. But to compute it efficiently without having to write that out 100 times and multiply, I'm going to use this rule. So here's another example. Now remember, every time you're doing a derivative problem, you always just ask yourself, do I have a rule for that? So I've got y equals sine of x times the square root of x cubed plus, let's say natural log of x this time. So again, I look at this function and I ask myself, do I have a rule for that? Well, first I notice, like, just almost, I heard a professor once say, you hold up the paper from far away, you look at it and squint. You're like, what does it look like? You know, just like, what is the basic form of this? Well, what I see is a product. I see a function of x, the sine of x, times the square root function. So my first inclination is to use the product rule. Now, in this function over here, I've got a sum of two continuous functions, and I've got a square root function on the outside of that. So we're going to have to use the chain rule for this piece. But initially, when we look at the whole function, and we just sort of stand back and squint and say, what is the form of this? I say, this is a product. And this is my first function, and this is my second function. So I'm trying to compute the derivative of a product. And that means the first thing that I will apply is the product rule. I have y prime equals the derivative of that product is the derivative of the first function times the second function undifferentiated. So you're just going to write it down. And then we're going to add the derivative of the second function times the first function undifferentiated. Now, anytime we see a radical, we want to remember our rules for exponent properties and rational functions. So if you have x to the n or m over n, that's the nth root of x to the m. And of course, that goes both ways. If you have the nth root of x to the m, you can write it as a rational exponent. We want to write this radical expression as with a rational exponent instead, so that we can apply our power. Now, with the square root, the 2 is implied, and we've got all of that raised to the first power. So the m is just 1 and the n is 2. So taking a square root of some expression is actually writing that expression to the 1/2 power. This is the 1/2 power. And the inside function there is x cubed plus natural log of x. So I applied the product rule because I noticed that the form of the entire function was just a product. And now with each of these, within each of these brackets, I know I have to compute a derivative. And the question I ask myself again is, do I have a rule for that? And yes, I do have a rule for that. Here's my rule sheet. The derivative of sine is cosine. We're just going to write that down. And then we'll multiply by this square root function. We're not doing anything to it. We're just writing it down. It's derivative of the first times the second from our product rule plus derivative of the second times the first. Now that sine function, we're not going to do anything with it. I'm just going to write it here for right now. But then for this one, I say, do I have a rule for that? And I don't have a basic rule for that. I don't have any rules for composite functions except for the rule that we just learned. So I'll apply the rule that we just learned. I've got this function nested inside that square root function or that 1/2 power function. So the derivative of a function raised to the 1/2 power is 1/2 of that function raised to the 1/2 minus 1. 1/2 minus 1 is negative 1/2. Then you want to put the inside function back inside. And then multiply by the derivative of the inside function by the chain rule. And I think I made a mistake here. I wrote a plus sign when I should have written multiplication. Now we just have to evaluate this expression and then maybe simplify it. We tend to like to write our rational powers with radicals rather than rational exponents, and we like to get rid of the negative exponents by putting expressions in the denominator as necessary. So we've got that there. And then this piece, the derivative of the sum is the sum of the derivatives. Derivative of x cubed is 3 times x to the 1 less power. 3 minus 1 is 2. Plus the derivative of natural log of x, which is 1 over x. I actually tell my students in class that when they're learning these rules to just write down the derivative, make sure you compute all the derivatives and then be done. Just don't do anything else to it. So at this point, I would tell my students to just stop. You've got that square root times cosine. That's 1/2 times this 3x squared plus 1 over x times sine of x. And because of that -1/2 power, and this property, x to the negative n is 1 over x to the n. That's actually 1 over that expression raised to the +1/2. And we can think of this as itself over 1. If we multiply straight across and replace that 1/2 power with a square root, we end up with this. Again, I would have my students just stop before this point, like right here. But if you're checking your answer in the back of the book, you want the form that's the most simplified. So we're going to have this. Now, one other thing that I noticed is that there's an x in the denominator and the numerator of the larger fraction here. So I might multiply by x over x to simplify even further. They've got x times this, not exactly a polynomial, but it's close to one. This expression with multiple terms. I'm going to multiply each of those by an x. So we end up with 3x cubed plus 1 over x times x, which is 1, times sine of x. And then in the denominator, we're going to have that 2 times the 1 times the x, which is going to give me a 2x. And this we can write as a radical expression. And that's what we have there. So that is the simplified derivative of that. This is a formula for the slope of that function at any x value in the domain. The domain on that one might be a little complicated. We can only take the square root of a positive number in the real number system. So we need x cubed plus the natural log of x to be positive. Then we multiply it by the sine functions oscillating between -1 and 1. So it might actually be kind of an interesting graph, but this is a formula for the slope of that. If I want to know the slope at x equals 1, I just plug in x equals 1 to this, simplify, and we would see what we get there for this slope. All right. Now you don't always have to use the chain rule. Sometimes you can use other rules instead. So here's another example. Let's say you've got y equals 2 over 3x cubed. You can rewrite this as 2/3 times 1 over x cubed. And that's 2/3 times x to the -3rd power. If I do that rewrite, the chain rule is not necessary at all. Then I can just, and I'm rewriting this expression using this rule, 1 over x to a positive power as x to a negative power. And I'm rewriting it so that I can apply my derivative rule. And that doesn't require the chain rule at all. So we've got 2/3 times what we get when we bring the power down, multiply by x to the 1 less power. The 3's reduce, and you end up with -2 times x to the -4th, or -2 over 1 times 1 over x to the 4th, which gives us -2 over x to the 4th. And that example is not even related to the chain rule, but I just threw it in there to make sure that you were thinking about what you were seeing. You could also apply the quotient rule here, but that would not be necessary either, because you can do the rewrite where you think of that 2 divided by, or that 2 over the 3x cubed as a fraction times that. So if you've got that constant times x to the -3, it's easier to just apply the power rule as opposed to using the quotient rule here, which is kind of a lot. Okay, so here's another problem. Let's use y equals secant cubed x. Okay, do I have a rule for that? We'll go to your rule sheet. I've got a rule for the derivative of secant at secant times tangent, but I don't have a rule for secant cubed. I'm like, well, I guess we could think of it as a product as secant times the secant squared if you want to. But I think it's easier to think of that as a composite function. Secant cubed x is actually secant of x quantity cubed. So we have an inside function and an outside function. Here's our inside function. The outside function is that cubing function. So the chain rule is appropriate. So here, when I compute my derivative, I just say, well, what's the derivative of the outside function? Or what's the derivative of a function cubed? It's 3 times the original function squared. We've identified the inside function as secant of x. So we plug that in. That's the derivative of the outside evaluated at the inside times the derivative of the inside. And the derivative of secant of x is secant times tangent. Now, it's convention to write the power of the trig function on the name of the trig function. So when I see the secant of x quantity squared, I'm thinking secant squared x. But I've got secant squared x times an extra secant, that's going to be secant cubed x. We could write secant of x quantity cubed, which means the same thing. Then we've got that tangent there. And that is the derivative of that right there. So we have that. Let's say we're asked to find the derivative of e to the cosine of x. Yeah, we've got that function nested inside of another function. The inside function is the cosine function. The outside function is the exponential. We know the derivative of an exponential is just that exponential. The easiest derivative we know. The derivative of e to the x is e to the x. So the derivative of e to some power is e to that power. Plug that inside function back in and multiply by the derivative of the inside. And the derivative of cosine is negative sine. Don't forget your angle. So we end up with negative sine of x times e to the cosine of x. And that is our y prime. Exponentials, we had radical expressions, we've got power functions. We had product rules that involved the chain rule. Let's look at one where we've got a quotient rule that involves the chain rule. So let's say we've got natural log of x squared plus, I'm trying to use a different trig function that we haven't used. Let's do cosecant of x divided by e to the 4x squared power. Well, that requires the quotient rule. So we remember that the derivative of high over low is low d high minus high d low over low low. So we get the bottom function times the derivative of the top function. That's low d high minus high d low all divided by low low. So you've got e to the 4x squared quantity squared. Now to simplify this denominator, you want to remember this rule from algebra. If you've got a power raised to a power, you multiply those exponents. So e to the 4x squared squared is e to the 4x squared times 2. So we're going to have an 8x squared in that denominator, or e to the 8x squared there. And then here and here, we have to think about that if we have rules for those. So this is natural log of a sum. We don't have any way of simplifying that. So I need to think about this differently. Do I have an inside function and an outside function? I do. The outermost function is that logarithmic function. The innermost function is that function there. That one's inside, the logarithm is outside. So we're gonna use the chain rule. They have that exponential and the derivative of a log. The derivative of a logarithmic function is 1 over whatever is inside. So it's x squared plus cosecant of x times the derivative of the inside by the chain rule. And then that logarithm, I'd like to have that exponential out front, so I'm just going to write the logarithm to the right and leave myself space to compute the derivative of the exponential. And this one has an inside function as well. If it's not just e to the x, if it's got something else inside of it instead of just an x, the 4x squared, that's when we need the chain rule. The derivative of e to some power is e to that power. So you leave it alone, put that 4x squared back inside, and then you multiply by the derivative of the inside by the chain. Now I'm almost done. I just have to compute this derivative and this derivative, and then I'll be done. We could simplify from here, but I would tell my students, don't worry about simplifying it. Just write it down. We're just making sure that we understand the chain rule at this point. So this and this are there. And then the derivative of this piece is the derivative of the sum. Derivative of x squared is 2x. And then the derivative of cosecant is negative cosecant of x times cotangent of x. And put all of that in parentheses because all of that is multiplying this. And then we're going to subtract e to the 4x squared times the derivative of 4x squared. So you have 4 times that exponent, which is a 2, times x to the 1 less power. 2 minus 1 is 1. So there's just an implied 1 there. Times the natural log of x squared plus cosecant of x. Taking all of that and dividing by e to the 8x squared. If you want to simplify it, you could multiply the numerator and denominator by this x squared plus cosecant of x to simplify just a little bit further. It will get rid of that fraction in that first expression, that expression that we're writing down first before we subtract this guy. But it really doesn't make it that much simpler. I would tell my students on a quiz or a test over the quotient rule to just stop here, or it would be a quiz or a test over the chain rule, but it's a chain rule involving the quotient rule. I would say just stop, but if you want to check your answer in the back of the book, or you want to simplify as much as possible, multiply by x squared plus cosecant of x. Make sure you add those parentheses there to remind yourself that that entire quantity is multiplying that entire quantity, and this entire quantity is multiplying this. It's because of that sum, because we're adding or subtracting things, we need the parentheses everywhere. Now I want to take all of this and multiply by that, and take all of this and multiply by that. Now, this expression times this gives us this times this. This fraction and that reduce. So we end up with an e to the 4x squared times 2x minus cosecant of x times cotangent of x. And then here, there's nothing to cancel. It's just this expression is sum of a polynomial and a trig function. So I think I'll just write that as a factor. I've got 8x times x squared plus cosecant of x. Then I've got that exponential e to the 4x squared there times the log of x squared plus cosecant of x. All of that is divided by e to the 8x squared times the quantity x squared plus cosecant of x. And that's as simple as it gets. I know it doesn't look simple at all, but it's as simple as it gets for that particular function. But we used the product rule, and then with it, or excuse me, the quotient rule, and then within the quotient rule, we had to use the chain rule for that piece and the chain rule for that piece. And we used the chain rule derivative of the outside evaluated at the inside times the derivative of the inside. And then we evaluated those derivatives of the inside. Make sure to put parentheses around it if your expression has multiple terms. And then you don't have to simplify, but it's always a good idea to simplify, so we simplify. All right. So here's another example. Now remember, whenever you're looking at one of these differentiation problems, you're just asking yourself, do I have a rule for that? Can I compute this derivative with simple rules? And of course, you're saying, okay, we do have all these rules. We've learned all of these basic rules for the derivative of a constant times x, a constant times a function, a power function, sums and differences of functions. We've learned all of these. And the question is, out of all of the rules that we have learned, like what is the simplest way to write this so that the differentiation process is as simple as possible? Okay, well, I could use the quotient rule here, but I've got a constant in the numerator. Since I have a constant in the numerator, it's simpler if I just factor out that constant and then think of this as 1 over that expression in the denominator. And then we can rewrite this with a negative exponent, because 1 over some quantity raised to a power is that quantity raised to the negative version of that power. This is actually x squared plus 5, or excuse me, x to the 5th plus 2x raised to the 10th power, or so in the denominator. So when we bring it up to the numerator, it becomes x to the 5th plus 2x raised to the negative 10th power. And now we can apply our chain rule. So I've got a constant times a function. So the derivative is a constant times the derivative of the function. And here's my inside function, and the outside is that power function with the negative 10 in it. So the derivative of a function to the negative 10th is negative 10 times that function to the negative 10 minus 1, which is negative 11. Put your inside function back in. And that's going to give us a negative 30 times 1 over that function raised to the 11th. Which gives me negative 30 divided by x to the 5th plus 2x raised to the 11th. And we would think of this as our simplified form, or you could think of this as negative 30 times that to the negative 11. Either one is fine as far as your simplified form is concerned, but we have a tendency to like to write these expressions with positive exponents as opposed to negative exponents. So if we see a negative exponent, we tend to write that expression in the denominator for a simplified form. Now here's one where you actually have to apply the chain rule more than one time. So again, you sort of back away and you look at it and you squint and you say, what is that? Now you might be tempted to think that this is a product, but it's not a product. This is the tangent to the 5th of this polynomial expression. It's not tangent to the 5th times that. You have to take the tangent of something. And this is actually the tangent of that number, or of that number, which is represented by that expression, raised to the 5th power. So if you wanted to, you could write it like this. This is tangent of x to the 10th minus 5x cubed plus 4, all raised to the 5th power. And then you see that you've got an inside function and an outside function. Now with this, you might be saying to yourself, okay, if I'm using the chain rule here, what is the inside function? What is the outside function? I see a couple of inside functions. I see this tangent is inside that power function, 3 raised to the 5th. I also see a polynomial that's inside the tangent function. So like, what's the inside function? Well, you want to think about the outermost function first. So this 5th power is the outermost function, and this is the inner function for that outermost function. So when we take the derivative, we look at the outermost function first, and we say, well, what's the derivative of a function to the 5th power? Well, it's 5 times that function to the 1 less power. 5 minus 1 is 4. Then you put the inside function back inside, and then you multiply by the derivative of the inside by the chain rule. And now, at this point, you sort of ignore this. You're going to keep writing it down because it's a factor of your derivative, but you're done with the computation part. You need to say, do I have a rule for this? So, well, yeah, I've got the tangent, again, of this polynomial. So I'm going to use the chain rule again. Here, my inside function is the polynomial function, and the outside function is the tangent function. And a trig function raised to the 4th power is just, we notate it this way, tangent to the 4th of x to the 10th minus 5x cubed plus 4. The derivative of tangent is secant squared. So the derivative of the outside is secant squared of the inside. So you plug it back in. Don't do anything to it, just substitute. And then multiply by the derivative of the inside. And the derivative of this piece can be found as the derivative of the sum of the derivatives. Is the power rule there. So this is 10 times x to the 1 less power, which is 9, minus 5 times derivative of x cubed, which is 3, times x to the 1 less power. And the derivative of 4 is just 0. So this is 10x to the 9th minus 15x squared. And that's one of our factors. We've got a polynomial times this trig function times this trig function times that 5. Because I want to be clear that this is not multiplying this. We're not doing this times this and then taking the secant and then squaring it and then multiplying it by this other thing. I'm going to put the polynomial out front. So this is 5 times 10x to the 9th minus 15x squared times tangent to the 4th of the original inside polynomial plus secant or times secant squared of the original inside polynomial. And that's our derivative. All right. Now, there was one example from the book that I liked. All of these were examples that I just made up. But there's an example from the book that looked kind of interesting to me. I think I'd like to do that here on paper and then graph it on Desmos.com. We've got y equals the cube root of x squared minus 1 quantity squared. So basically we're taking x squared minus 1, which is the graph would be a parabola. Then we're taking all those values and squaring them. So we make them positive and then we're taking the cube root. Now, if we wanted to, we could write this as x squared minus 1 to the 4th power. It's the 2/3 power. That goes in the numerator of our rational exponent. That number goes in the denominator of our rational exponent. And so we might want to graph this function and then think about the slope at various locations. Well, x squared minus 1 is equal to 0 at x equals 1 and x equals -1. When x is equal to 0 here, and I get -1. -1 squared is 1, and the cube root of 1 is 1. And then I think what we're going to see is something like this. And there's some symmetry. Oops. Because we're squaring something and then cubing it. Okay, let's look at the graph to see if it actually looks like this. Now, before we do that, actually, let's compute the derivative. Here's our inside function. And again, the outside function is that power function. We're using power functions a lot in this video. The derivative of a function raised to the 2/3 power is 2/3 of that function raised to the -1/3. Put the inside function back in. And then multiply by the derivative of the inside. This derivative is just 2x. 2x minus 0, which is just 2x. 2x times the 2/3 is going to give us a 4/3 times x squared minus 1 to the -1/3. And if you want to, you can simplify this way. As x squared minus 1 to the +1/3 in the denominator. If you multiply straight across, you get 4x divided by 3 times this expression to the 1/3, or if you want the cube root of x squared minus 1. So the derivative is going to have asymptotes at x equals ±1. And then we'll see different values of the derivative in each of these intervals from -infinity to -1, from -1 to 1, and then up to infinity. So let's look at the graph on Desmos for that. Okay, so these are our graphs. This is y equals x squared minus 1 to the 2/3 power. Actually, maybe I should make my grid the same. We're gonna let X go from -20 to 20 and Y go from -20 to 20. It looks like that. But the interesting things are happening like very, very close to the origin. So I'm gonna zoom in a bit. And I noticed that graph is consistent with the graph that I drew on my paper. And we notice also that the function has cusps in it. And it's because we took something, we squared it, and then we took the cube root. Squaring it made it positive, and then taking the cube root sort of led to these sort of cusps. We got a different derivative from the left than we do from the right. The derivative from the left of x equals -1 is negative, but the derivative from the right is positive. We draw those tangent lines, we're going to see positive and negative slopes, negative slopes to the left of -1, positive slopes to the right. When we take the derivative by hand using the chain rule, we got this, and the graph looks like this. Notice that the denominator is equal to 0 at x equals ±1. So if I graph those lines, we see the vertical asymptotes of the derivative graph. And what I'm really interested in is the tangent line. So I want to graph a point x naught, f of x naught. So they're at x naught equals 1, the y value is equal to 0. I think I want to have f of x naught just shown right there, and f prime of x. See, it's undefined there. And then let's move that point around a little bit. So at that location, at x equals 0.3, the y value is 0.939. In addition to plotting that point, I'd like to plot the point that gives us the slope. So the slope is approximately negative 0.413. So we're right there, and it might be nicer to just see, well, actually we've got the y value for the slope right here. So we have the function value with the slope value, and we've got plotted those 2 points. I'd also like to see the tangent line. So let's graph the tangent. Tangent is y equals the original y value plus the slope, which is change in y over change in x, which is given by the derivative at x naught. And then we'll multiply by the change in x, which is x minus x naught. And let's make that tangent line a different color. There we go. So the claim is the slope of this line is negative 0.413 approximately. And just estimating by looking at that graph, it looks like I go down approximately 1. It's a little bit less than 1. And then we run to the right, however many units that is. And see, the line intersects there. It's very, very close to intersecting at x equals 2. So I'm going to say this is this is 2/10. This is 0.2, 0.4, 0.6, 0.8, and 1. This is like 0.3. And that's 2. So this distance from here to here is just going to be about 1.7. And then the distance from here to that 1.7-ish is going to be 0.2, 0.4, 0.6, and I'd say 0.68. So I think we're going down at negative 0.168, and then we're running to the right 1.7. So I go negative 0.68 divided by 1.7 is approximately 0.4, which is what we get when we look at the derivative value. The value of the derivative at that location is about negative 0.4. So our calculations are consistent. So it looks like our graph, at least for that point, is giving us the correct slope. The graph of the derivative is giving us the slope of the tangent line at that particular location. And as usual, we can always move that x value around, get different slopes. We have positive slopes to the on the interval from -1 to 0, get a 0 slope at the top there, negative slopes here. And that's consistent with this graph. Those slopes are all positive here. And notice that the slopes are getting increasingly steep as x approaches -1. We're sort of getting steeper and steeper. Actually, I just want to, let's look at the interval from -1 to 1. If we stay on that interval, we can see how the line just keeps getting steeper the closer we get to that -1. And then we still have positive slope, but the slopes are getting, or the lines are getting less steep until we get to 0. Then we've got a 0 slope, horizontal tangent line. And then as we go from 0 to 1, the slopes are negative. And so the values of the derivative are negative. And those lines just keep getting steeper and steeper, more and more negative as we approach -1. And then we could do something similar on these other branches. Let's say from -4 to 1 or -1. Pick an x value over there. These all have negative slopes. And then if we want to go on the other side of one of these little cusps from 1 to 4. Move that slider and we see those graphs. Those slopes are all positive and the derivative values are positive. So I hope that helps. I hope that gives you a better understanding of our graphs. This teal graph is the original function and the orange graph is a derivative. And the tangent lines are all negative here, so the derivative has negative values. The tangent, or the slopes of the tangent lines are negative here, excuse me. So the derivatives have negative values here. The tangent lines all have positive slopes, so our derivative values are positive. X equals 0, we get a horizontal tangent line, so our derivative is 0. And then from 0 to 1, all of our tangent lines have negative slopes, so we get negative values here. And then from 1 to infinity, our tangent lines have positive slope, and slope is given by this branch of the derivative graph. But how did we compute it again? We used the chain rule. First, we had that expression involving the third root. We rewrote it as the polynomial to the 2/3 power. We took the derivative using the chain rule and then rewrote it so that that exponent, that -1/3 exponent corresponded to this factor in the denominator. Then we just graph them and then use the tangent line to verify that the slope of the tangent line and the derivative value are the same thing. So that's it. Now let me know if you have any questions. Might do the derivation of the chain rule algebraically in another video.